Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back to Optimization in Civil Engineering. In the last few lectures, we discussed about the linear programming problems. In these linear programming problems, you came to know about the linear functions and you also learned how to use the graphical method to solve the linear programming problems. We also discussed that the graphical solution is feasible as long as the number of variables are 3. In case the number of variables are more than 3, it is difficult to visualize and hence the graphical solution may not be convenient to implement. For those reasons, we said that there is another method called simplex method that can be employed to solve the linear programming problems. Now, in certain special cases, there are certain variations in the simplex solution methods. In those variations, we saw that if we have equality constraints or greater than equality constraints, the one which does not follow the standard format of the linear programming problem, we need to employ either the two-phase solution method or we need to employ the big M method. Either way, we could solve the problem and get our answer. We also discussed about certain cases where there are multiple solutions or the function is unbound and we are unable to obtain the solution. We'll also find that apart from simplex method, there are other methods to solve the linear programming problem. Those are beyond the scope of this syllabus and hence not going to be discussed in this class. However, in linear programming problem, there is one property that needs to be discussed, and this property is known as duality in the linear programming problem. In today's lecture, we are going to discuss about the duality in the linear programming problem. The duality theory indicates that every LPP problem can be associated with another LPP or linear programming problem known as the dual. In this case, the original linear programming problem is known as the primal. The duality of LPP is useful in interpretation and implementation of sensitivity analysis. So whenever you are finding out a solution, you would also need to know how long the solution is valid or whether the solution is valid in case there is a change in the variable coefficient or the constraint. For this, it is always required to do the sensitivity analysis and the duality of the LPP can be used for that purpose. So in order to understand the primal problem and the duality problem, here is an example how it is represented. A primal problem where we are maximizing, which is our standard format, can be represented as given here with the constraints which are indicated here. The corresponding dual problem is going to be the opposite of the primal, which is minimization, and is represented as given here with the constraints as shown here. Now here one thing you will notice that the coefficients which was there for the decision variable or the design variable, that is this C, is actually now part of the constraints in the dual problem. On the other hand, the constraint which was there in the primal problem is now the coefficients of the objective function in the dual problem. So let us understand this through an example. In this example, we have the primal problem in a standard format which is indicated here. The corresponding dual problem is represented here. The coefficients of the objective function, this 3 and 5, are now part of the constraints as 3 and 5. So another thing to notice, not only the objective function is going to be minimized for the maximization problem of a primal, the constraints which in the standard format was less or equal to is now greater or equal to in the dual problem. Now the constraints in the primal problem, the constant part is now the coefficient in the dual problem. We need to reconstruct the constraints in the dual problem. For that reason, we are using a new set of variable which is known as y. So we are first of all multiplying each of these constant part of the constraint in the primal with y1. So the next one is 12, which is here, multiplied with y2. The third one is 18, which is here, multiplied with y3. While reconstructing the constraint of the dual, we have to deal with three variables, y1, y2, y3. For that purpose, we look into the constraints of the primal. So in the constraints of the primal, the first constraint is associated to y1, the second one is associated to y2, and the third one is associated to y3. When we are reconstructing, we are writing it as y1, and the presence of x1 is again in the y3, so we write it as 3y3. So we keep this coefficient in the dual. Then in the second one, which is for the x2, we can write, in the first case there is 0x2, so there won't be any y1. In the second case, we have 2x2 that is related to y2, so we are saying 2y2. And in the third case, there is 2x2 that is related to y3, so we are saying 2y3. Since there is no x3, so there is no third constraint. So one thing to notice is that the number of design or the decision variables we have in the primal is going to dictate the number of constraints we are going to have in the dual problem. And the number of constraints we have in the primal problem, in this case 3, is going to dictate the number of design or decision variables in the dual problem. In a nutshell, the properties of the problem formulation, will see that the coefficients of the objective function in the primal problem are the constants on the right hand side of the constraints in the dual problem, which we saw here. The right hand side of the constraints in the primal problem is 4, 12 and 18 are the coefficients of the objective function in the dual problem. So here 4, 12 and 18. And the third property is the coefficients of a variable in the constraints of the primal problem are the coefficients in a constraint of the dual problem. These coefficients 1, 2, 3, we are retaining those coefficients, so 1 and 3, so 2 and 2, 2 and 2. So that is what the third property indicates. Now another thing you might notice here is that the primal problem is a maximization, whereas the dual problem is the minimization. Basically the primal and the dual are optimized, but one is maximized and the other is minimized. The feasible solution for a dual problem are the one that satisfies the optimality condition of the primal problem. So that is the only solution in the dual problem that is valid for the primal problem. In other words, the optimal solution of the primal problem is the feasible solution of the dual problem. We can clearly see that the maximum feasible value of primal problem is going to be the minimum feasible value of the dual problem. This is the reason we maximize the primal and we do the opposite, that is minimize the dual problem. The primal and the dual follow certain relationship, and these relationships are weak duality. For any feasible solution of the primal and the dual, we'll see that the objective function in the primal is going to be less or equal to the objective function value of the dual, provided the solution is a feasible solution. And this property is known as weak duality. A strong duality is the property where optimal solution of primal and dual are going to be equal. So this is an extension of the weak duality when we see that the feasible solution in both cases are optimal solution, then we see that the objective function value of the primal and the dual are going to be equal. The third relationship is known as the complementary solution relationship. In this case, the simplest method yields a feasible solution for the primal or dual, and for that solution there exists a complementary solution in the corresponding dual or primal such that the objective function values are going to be equal. In this situation, it is to be noted that if the solution x in the primal or the solution y in the dual is not the optimal solution, the corresponding y in case of primal where y is in the dual or x which is going to be in the primal is not a feasible solution. So we have a primal and we have dual. We have a solution here which is x and the corresponding solution here y in such a way that the objective function values are going to be equal, which is indicated here. In that case, if this is not the optimum solution, then we can clearly say that the corresponding solution y is not going to be a feasible solution. If we are looking in the reverse way, which is in the dual, if we have a solution y and for that we found out a solution x at which the objective function values are same, then if y is not the optimal solution, x is not going to be a feasible solution. So it works both way. This is one property which will come later for the understanding. This is what the complementary solution relationship means. However, if the complementary solution is an optimal solution, so that relationship is known as complementary optimum solution. In that case, if x in primal or y in dual is the optimal solution, the corresponding y in dual or x in primal is also the optimal solution. So this is in connection with the strong duality. If one is optimal, the other is also going to be the optimal. That is what the complementary optimal solution is going to indicate. If we see the strong duality, if one is optimal and the corresponding objective function value, whatever we get, is equal to the objective function value what we can obtain in the dual for a particular solution y, that y is also going to be the optimal solution. With this, we also know that if we go the reverse way, if we start with the dual problem and find out the optimal solution y star and find out the objective function value, and for that same objective function value, whatever x value we get in the primal problem is expected to be the optimum solution. So the complementary optimal solution relationship validates the strong duality relationship. And the fifth relationship rule says that the relationship between primal and dual problems are symmetric, as dual of a dual problem is the primal problem. So this symmetry relationship is important because if we do the dual of the dual, so if we do the dual of this particular problem, it is going to be nothing but the primal which we had started with. So whatever relationship or whatever characteristics are there between primal and dual is also valid for the dual to primal, and that is what the symmetric relationship indicates. Let us understand this through an example. So here we are taking the same example where we have the primal problem here and the dual problem which is indicated here. Now in case of weak duality, we say one of the feasible solution of the primal x is going to 3, 3, which is x1 is 3 and x2 is 3. we'll see that it satisfies all the constraints and hence it can be a feasible solution. However, it might not be the optimal solution. In this case, the objective function value is going to be 24. And if we want to find out a feasible solution in the dual problem, and that solution is 1, 1, 2, which is y1 is equal to 1, y2 is equal to 1, and y3 is equal to 2, which satisfies all the constraints. Of course, it is not the optimum solution. And if we find out the objective function value, we'll see that the objective function value is 52. In this case, as per the weak duality, it is going to be greater than the objective function value of the primal problem. This is what we see here. When we look into the strong duality, we find out a solution 2, 6, which happens to be the optimum solution in the primal. And for this, the objective function value is 36. And the optimal solution in case of dual problem, we see the value of y1 is 0, y2 is 1.5, and y3 is 1. And this is the optimal solution for which the objective function value is also 36. As per the strong duality theory or relationship, we can say in case of optimal solution in the primal and the dual, we are going to obtain the objective function value as same. Now if we look into the complementary solutions, in which case the objective function values are expected to be same, then if we choose a feasible solution in case of a primal, which is 0, 6, in this case we have chosen, and the corresponding dual solution is going to be 0, 2.5 and 0, for which the objective function values are expected to be same, then we can clearly see that even though this point is feasible in the primal, this is not feasible solution in the dual. So that is what the complementary solution relationship indicates. We can see the reverse way. We can choose a feasible solution in the dual and find out the objective function value. For the same objective function value, if we try to find out the solution in the primal, we'll see that particular solution is not feasible. The fourth relationship, we talked about the complementary optimal solution. And in this case, if we see that the optimal solution, which in the strong duality, we use that particular point, the complement optimal solution is going to be this, and which also happens to be the optimal solution of the dual. So complementary optimal solution are valid as long as the solution in primal as well as the dual are feasible and optimal. And as we say that the reverse is also applicable, so there exists a symmetry between the two sets of problems. Digging deep into the duality theorem, we can say if one problem has feasible solution with bounded objective function, then the other problem has same characteristics, means it will be also have a feasible solution with bounded objective function. In this case, both the weak and strong duality properties are applicable and valid. On the other hand, if one problem has feasible solution with unbound objective function, then we'll see that the other problem, which is the dual problem, has no feasible solution. However, if one problem, for example the primary problem, has no feasible solution, then we'll find the other problem, which is the dual problem, has either no feasible solution or we may get into an unbound objective function. So let us understand this duality theorem through an example. In this case, we have a primal problem which is indicated here. The dual of this problem is going to be indicated here. Now here you will notice that we have used greater equal to sign. If we multiply with -1 on either side, then we can change this sign to be less equal to and bring the problem into a standard format. So once we bring that problem into standard format, this value is going to be -65, and that is the reason you see it as -65. Since we are multiplying with -1, so this is going to be -1.5, that is what you see it here. This is going to be -1, so that is what you see it here. In this case, you will see that the primal has feasible solution, but the objective function is unbound, and hence we may not, or we do not get the optimal solution. In this situation, if you look into the dual problem, it can be easily plotted in the graph. The graphical solution will clearly indicate us that the dual has no feasible solutions. So this is one of the duality theorem which we discussed earlier. We'll also look into another example. In this case, we have the primal problem which is indicated here. We have greater equal to sign in the constraints. Now we know how to convert it into a standard format. And once we convert it into a standard format, the dual problem is going to be like this. In this case, you will notice that the primal has no feasible solution. If we try to represent it in the graphical format, you will see that the primal problem has no feasible solution. Hence, when we investigate the dual problem, we'll notice that dual has feasible solutions with unbound objective function. This is exactly what we discussed in the duality theorem a little while ago. Now, this duality has some important use, and that use we'll discuss now. To understand that use, we need to understand the economic interpretation of the various components in the primal problem and the dual problem. In the primal problem, we have the design or the decision variables x. Those variables represents the level of activity within the problem. Then we do have the coefficients in the objective function. Those coefficients actually represents the profit that can be earned from each of this activity, which is indicated by C. When we estimate the objective function value, that indicates the total profit from all the activities applicable. Then we do have the constraints, and on the right hand side of the constraint we have a constant, and this constant B represents the amount of available resource for the activity which we want to perform. And on the left hand side we have the coefficients of the variable in the constraint, and this coefficient A represents the amount of resource that needs to be consumed by each activity. Now, when we convert this problem into a dual problem, we do have a new set of variables which is y, and this y represents the contribution to profit per unit of resource. We have limitation on the resource, and in case we are trying to optimize, we need to see how this resource contributes to the profit, and that is what it is being done in the dual problem. And hence it is actually the shadow price of the variables which we have considered, or the problems which we have considered. With this understanding, let us look into the primal and the dual problem. As we had indicated, the primal problem can be represented here and the dual problem is represented here. The C, which represents the profit from each activity which was there in the primal, has now become the right hand side of the constraint in the dual problem. So the profit from each activity is now being represented as the amount of available resource. So in the dual problem, we can clearly see that this resource can help us to understand to what extent the solution which we have obtained in the primal problem is going to be valid. If it is valid in the dual problem, then only the solution is going to exist even if we change the profit from each activity in the primal problem. So in many cases, it happens after solving, we need to revisit the problem because there could be a change in the profit of the activity over time, and in that case we can quickly look into the dual problem and see if our solution is still valid or not. Likewise, we can see the changes in case of available resource which is indicated in the primal problem and become the factor or the coefficients in the dual problem objective function to see what extent this can affect the optimal solution or the optimal objective function value. So in vice versa, we can always compare and understand whether our solution is still valid when we are looking into the primal and the dual. This is going to fall under the sensitivity analysis of the parameters. For that, we have the application of sensitivity of the primal and the dual. We need to understand that. So if we see any changes in the available resource which I was talking about, it is going to change the objective function of the dual problem. We can quickly look into that, how the objective function value in the dual problem is going to vary, and if we know how it is varying, we can easily say what is going to be the total profit with the change in the resource. We do not need to solve the problem again, provided the solution is still valid. We can also use this property to understand what are the allowable variation in the available resource is permitted. The dual problem can be explored in that case to review the effect of that. So that is going to tell us how much variation it is going to bring to the objective function value. In order to understand this little bit in depth, let us go back to the problem which we had discussed here. So if we increase the resource here, it is clear when we come to the dual problem, we can see that there is an increase in the objective function value, which means as per the strong duality, the objective function value of the primal is also going to increase. Means overall profit is going to increase, provided our solution is still valid. Likewise, if we decrease the resource, the objective function value in the dual problem is going to decrease. Likewise, as per the strong duality relationship, we can say the objective function value of the primal is also going to decrease, provided the solution is still valid. If we want to see to what range we can play around with the resource, we can say how we can change this B and still have a valid solution. Once we get that, we can always put it back in the dual problem and see what is the range in the total profit is happening, which will be applicable for the primal problem. So going back to the sensitivity analysis, we can say that any change in the resource is going to help us to quickly estimate the change in the total profit through the dual problem, and the allowable variation in the available resource is also going to help us to estimate the variation in the total profit through the dual problem. Now we may need to also look into the changes in the profit from each activity of the non-basic variable. Sometimes the non-basic variable, if we are changing the profit, then we need to see what is the effect. The validity of the constraint in the dual problem can be evaluated in that case. So if I have to go back to the problem again, if we have certain variables which were non-basic, the associated coefficients C is going to be the right hand side of the constraint. So we have to quickly look into whether the particular constraint in the dual problem is still valid for the given solution. If it is still valid, then no matter what the change is in C, our solution is still valid. We do not need to resolve the problem. Now, in the similar way, we can use the allowable variation in the profit from each activity of non-basic variable, and we can use the dual problem to explore and see to what extent this can be varied. Particularly with this new variable, it is going to create a new set of constraint, and once we review that constraint, we can clearly see that what is the effect of the new variable. We can also look into the changes in the profit from each activity of the basic variable. In this case, we may need to solve the problem again, and that can be quickly investigated again in the dual, whether the solution is still valid or not. If the solution is still valid, we may not need to resolve, otherwise we have to solve the problem again. There could be a situation when we may need to introduce a new constraint in the primal, and if we do so, we have to quickly look into the optimal solution that satisfies the new constraint in the primal problem. So by some simple investigation, it is going to save us the whole process of re-evaluating the problem for the optimal solution. And this part we can do it by collectively looking into the primal and the dual problem and understanding the sensitivity of the parameters. So with this, we'd like to conclude the duality property. You can investigate the duality property through certain examples and see how it is going to vary and what is the impact of that in the solution. So in today's lecture, we learned about the duality theory of the linear programming problems. This understanding is going to be very useful in case when you are solving the real world problems. For example, if you are solving a problem where you need to optimize the objective function which depends on the cost of the raw material which is being procured. Once you solve the problem and you found out your solution for all the constraints you have, now you find out that there is a change in the cost of the raw material. Then do you think your solution is still valid? Well, the obvious case of that one would be you solve the problem again and find out whether the solution is valid or not. That is going to be a time consuming process, particularly if the problem is very large and it's going to take a lot of time. The quick way of looking into that is if you can form the dual of the primal and investigate the constraints based on the revised cost of the raw material and see if it is still valid, then you can clearly say that your solution is still valid. You can actually look into that in other cases as well. For example, if there is any change in the constraints, for example, if your storage capability got enhanced or reduced, so that is part of the constraint when you are procuring the raw material and using it for the production. If it is enhanced, which means you have more capacity to store certain raw materials, then you need to see whether it is going to actually affect the profit or not. You can quickly go to the dual problem and look into the objective function value of the dual problem and see whether it is increasing or decreasing or what is the effect of that. This way you can decide in such problem what is good for the project and what is not by a quick investigation of the primal and the dual accordingly. This type of information are going to be very useful large problems or complex problems. With this, we are going to conclude today's presentation on the duality of the linear programming problem. In the next lecture, we'll investigate or we'll look into a special case of linear programming problem, which is a transportation problem, and a variation of the transportation problem, which is assignment problem. With that, thanks to all of you for listening and see you in the next class.